Hello. So, we will discuss the least upper bound, greatest lower bound of a set and compact sets today. So, this requires the concept of ordered set first. We define like this, let S be a set S be a set, an order on S is a relation denoted by sign, this sign which we call, later on we will say less than sign or smaller sign, with the following two properties. The first property is that if x is in S and y is in S, then one and only one of the following statements that is x is less than y, x is equal to y and y is less than x is true. And second one is, say, if x, y, z, they are the elements of S, and if x is less than y and y is less than z, then x must be less than z. So, if a set S together with this operation which we call it together with this relation less than sign satisfy these two property, then we say that this is an order on S. This sign less than sign, we normally say x related to the means x is smaller than y. And the negation of this is x is greater than or equal to y. This is the negation part of it, means x is greater than or equal to y, the negation of this will be x is strictly less than y. So, that will be the sign for them. Now, obviously, when we say the set of rational number or set of the real numbers, then this order is defined. One can identify two real number or two rational numbers, one can say which one is smaller than the other, or whether they are equal or whether one is greater than the other, like this. Then the order set means a set, an ordered set S, order set is a set S in which an order is defined, For example, set rational number, set of all rational numbers is an ordered set, because if we take R and S, suppose these are two rational number and define the relation R is less than S, means S minus R is a positive rational number, then obviously it will satisfy these two property which you have stated. So, set of rational number is an ordered set, set of real number is an ordered set, set of real number is an ordered set, ordered set. However, set of complex number, set of complex number is not an ordered set. We cannot introduce the order between the two elements of a C complex number, set of all complex number, because for example, if suppose I take the complex number e and 1, okay, and when we say e is greater than 1, okay, e is the element say square root of minus 1, this is e, or I will say I, if you I, this is a complex number. So, I is greater than 1, it means it is positive, we are assuming. So, I into I is still greater than 1 into 1, that is I square is minus 1 is greater than 1, which is a absurd. It means our ordering which you have introduced is not correct. Similarly, one can show whether if I is less than 1, we can again lead a contradiction and like this. So, we are unable to introduce the order in the over the set of all complex number, that is the set of a complex number is not an ordered field. Field we will discuss in algebra or some. Okay. Then we are interested in particular in defining the least upper bound and the greatest lower bound. So, let us see first what is an upper bound and lower. Suppose S is an ordered set, S is an ordered set and E is a non-empty subset of S. Now, if there exists some beta, there exists a beta in S such that all the elements of E, that is x belongs to E, is less than or equal to beta, and this is true for every x belongs to E. Then we say E is, then we say beta is a or E is bounded above, E is bounded above, okay, and beta is an upper bound and beta is known as upper bound for E. Now, obviously, beta is an upper bound, there are many infinitely many real numbers will be available which will be an upper bound for E. Any number which is greater than beta will act as an upper bound for E. Okay. So, we are interested in the least upper bound for it. The same case happens if it is lower bound. We define the lower bound in a similar way. Suppose S is an ordered, suppose S is an ordered set, and E is a subset of S, non-empty subset of S. If there exists a number say gamma belongs to S such that gamma is less than equal to x for every x belongs to E, then we say E is bounded below and gamma is the lower bound is a lower bound of E. So, there again there will be many lower bound available as soon as you take any number less than gamma, which will also behave as a lower bound. So, we will be interested in knowing what will be the greatest lower bound of the set E. So, we introduce the concept of the upper bound and lower bound as follows. This is the concept of least upper bound. Okay. Suppose S is an ordered set, S is an ordered set and E be a non-empty subset of S, and also assume E is bounded above, E is bounded above. Now, suppose there exists an alpha belongs to S with the following property. Alpha is an upper bound of E. This is the first property, and second one is, if I take a number slightly lower than alpha, then it should not behave as an upper bound, and second is, if gamma is any number less than alpha, then gamma is not an upper bound of E. Okay. So, E is a bounded above and alpha is such a number which is an upper bound of this, but if we take a number slightly lower than alpha, then that number will not behave in upper. It means, alpha is the least upper bound for E. Then alpha is called the least upper bound of E, and we denote this thing as, and also, or some we also say it is a supremum of E. And we write that least upper bound of set E is alpha, or it is the same as when we say supremum of E. The similar way we define the greatest lower bound. In a similar way, we can introduce the concept of the greatest lower bound of E. So, what we assume is, suppose S is an ordered set, S is an ordered set, E is a subset, non-empty subset of S, and E is bounded below, below. Suppose there exists and say beta belongs to S, a beta belongs to S with the following property, properties. The first is, beta is a lower bound, of E, Second one is, if a number, if I choose, if a number say delta which is greater than beta, then delta is not an is not a lower bound of E, is not a lower bound of E. Okay. So, if we take any number delta slightly higher than this, it will not be lower bound. Then this beta, then beta is known as greatest lower bound of E, or we can also say it is the infimum of the set E, and we denote this as beta is the infimum of the set E, or is the same as the greatest lower bound of E. So, this is the way we define the greatest lower bound and upper and the least upper bound, greatest lower and least. Now, let us take an example. Suppose I take the set A, let A be the set of all positive rational number P. P is positive rational number. So, it is positive rational numbers such that P square is less than 2, and let B is the set of all positive rational numbers such that P square is greater than 2. P square is greater than 2. Now, if we look at A and B, A is the set of all positive rational number whose square is less than 2, and B is the set of all positive rational number whose square is greater than 2. Obviously, A is bounded above. In fact, all the elements of B will be the upper bound, will act as an upper bound for A, but A does not have the least upper bound, because we can't get the rational number which is for which we can say is a really a number which is a least upper bound for it. Similarly, for the B, if you look the all the elements of B satisfy this condition, then it has a lower bound, and all the elements of A behaves as a lower bound of this plus all rational number which are negative or 0 will behave as a lower bound for this, but neither A nor B has an upper bound and the greatest lower bound. Okay. So, this will show that A contains no largest number and B is clearly A contains no largest number, while the B and B contains no smallest number. Okay. So, in this case the greatest lower bound A has no greatest B has no greatest lower bound and A has no largest number. So, this so therefore, we can say A has no least upper bound, while the B has no greatest lower bound. That is obviously true. Okay. Let us take another example. Suppose I take the set of rational numbers, let E1 be the set of all rational number R belongs to Q such that R is strictly less than 0, and E2 be the set of all rational number Q rationals such that R is greater than equal to 0. Okay. R is less than equal to 0, same, such that R is less than equal to 0. Suppose I take this thing, then the set of rational number which are less than 0. So, obviously, it has an upper bound 0, here also has upper bound 0. It means the supremum value of E. So, therefore, supremum of E1 will be 0, supremum of E2 will also be 0, but you see the supremum value of E1 does not belongs to E1, while the supremum value of E2 belongs to S. So, it is not necessary when we say the least upper bound or greatest lower bound, then it is not required, it is not necessary that that supremum value will be a point of set. It may or may not be the point of set that we have observed here. Okay. Similarly, but both are having the same. Okay. Similarly, now another interesting property which is in connection with the order set is, this is known as the least upper bound property. Least upper bound property. What is the least upper bound property? An ordered set S is said to have the least upper bound property if the following is true. Following is true. What is therefore, if E is a non-empty subset of S, is not empty, is a non-empty subset of S, and E is bounded above, then the supremum of E, that is least upper bound of E, will exist and exist in S. So, this is the least upper bound property of a set. An order set S is said to have a least upper bound property if the following is true. That is, if we take any subset, non-empty subset of A which is bounded above, then supremum E exists in S, then we say this set S is a least upper bound property. If for any set this supremum does not exist, then the set will not have a least upper bound property. For example, set of rational numbers, that is which is denoted by Q, does not have least upper bound property. And that we have seen already with this example, because basically A and B, these are the two subsets of the rational numbers, and neither the A nor B has an upper bound, is it not? Neither A does not have a upper bound, B does not have the lower bound for it. So, basically the set of rational number you can say does not have a least upper bound property. Now, there is a relation between the greatest lower bound, least upper bound, and the least upper bound property. In fact, it is shown that if the set is having the least upper bound property, then it must have a greatest lower bound property also, and that can be judged in the next theorem. The relation between the least upper bound, greatest lower bound, and this. So, theorem says, or you can, before this you can write the remark. I will write the remark here is every ordered set, there is a relation between the greatest lower bound, that every ordered set with the least upper bound property, upper bound properties with the least also has their remark is there is a close relation between greatest lower bound and the least upper bound, and that that every order set with the least upper bound property also has the greatest lower bound property. This can be seen with the help of this result. The theorem says that if suppose S is an ordered set with the least upper bound property, and suppose B is a non-empty subset of S, B is a non-empty subset of S having, and B is bounded below. So, S is an ordered set which has a least upper bound property, and a set B has a property which is bounded below. Now, these together will implies the least relation between the greatest lower bound property. Okay. So, what it says is if B is bounded below and let L be the set of all lower bounds of B, then the supremum of B, that is the least upper bound of B, that is alpha, will exist in S, and this alpha will be the infimum value of B, that is it will be the greatest lower bound for B. And in particular, infimum of this V exist in S. Okay. Infimum. Let us see the proof of this. What is given is S ordered set which has a upper bound property. Upper bound property means if any set is there which is a subset, non-empty subset of this, and if it has an upper bound, then the supremum of this will exist in this. Now, here we are assuming that S has a upper bound property and a non-empty subset B is bounded below. Then because of this upper bound property and this condition, we will show that B will have the greatest lower bound and infimum of B will exist in S. That is what is. So, since B is given, B is bounded below. This is given. Okay. And what is our L? L is the set of all lower bound of B. B is bounded below, is already given. It means there is a bound available. So, L is non-empty. So, this implies L is non-empty. Okay. Now, L is the set of all lower bound of B. So, what is L? So, clearly since L is the collection of, L is the set of all lower bounds of B. So, basically L consists of those by, it means L is the set of those points in S, by in S, such that by is less than equal to x for every x belongs to B. Because L is the collection of a lower bounds. So, the by is set less than equal to x, then by will be the lower bound for B, and or such by will satisfy this condition will come in the class L. Okay, and this will be a non-empty set. This one thing is clear. Now, every x. So, if we look the L, L is the collection of those points which are less than equal to x for every. It means every point of B behaves as an upper bound for L. So, clearly every x in B is an upper bound of L. So, it means L is bounded above, thus L is bounded above. So, L is a non-empty set which is bounded above, it is a subset of S. L is a subset of S. So, bounded above and is a subset of S, is it not? S in order. So, we can apply the property because S is an order set having the least upper bound property. So, by the property, since S has a least upper bound property, so by this L will have a supremum value. So, L has a supremum value in S, exists, supremum value will exist, and let it be, let alpha is that supremum value of L is alpha, suppose supremum value of this alpha is that. Okay. Now, if we choose gamma, if gamma is any number less than alpha, then gamma is not an upper bound of L. Because alpha is the least upper bound. So, if we take any number lower than gamma, lower than alpha, then that cannot behave even a upper bound for it. Otherwise, gamma will be the least upper bound. Okay. So, gamma if it is less than alpha, it cannot be an upper bound. Hence, what is our B? B is the set of those points which are for such that every point of this is an upper bound for it, and here gamma is not coming in an upper bound for L. So, obviously, gamma cannot be a point in B, because all the points of B must be an upper bound, is an upper bound which we have shown, but gamma is not an upper bound of L, therefore, gamma cannot be a point of B. Okay. So, what this follows, it implies that alpha is less than equal to x, alpha is less than for every x belongs to B, because any number less than alpha cannot be a point in B. So, alpha will be the least number and then alpha will be less than equal to x. So, this shows that alpha belongs to L. Okay. That is what alpha belongs to A, that is the supremum will exist and it is in L. Now, if any number which is less than alpha, any number beta which is greater than alpha, then beta cannot be in L, because alpha is the least upper bound and all the beta is greater than. So, again it will not be in L. So, once it is not in L, alpha is not in L, beta is not, then what happens? That this beta which is greater than alpha, in other words, that alpha will be the infimum value of B, because then beta will be in which? Beta will be in B. So, it is a alpha beta. So, this shows alpha is a lower bound of B, is a lower bound for B, but beta is not, as if beta is greater than alpha, it will not be lower bound for this, okay, because it is the least. Therefore, alpha will be the infimum of B, and that proves the results. Okay. So, that shows the result. Now, having proved this thing, we will come back again to the sets where we are discussing the open sets and closed sets, etc., where the supremum value, infimum value will be required. So, we need basically we wanted to show that result where the supremum concept and infimum concept is required. So, that is why all these things were taken. So, this result we wanted to show. The result is, let E be a non-empty set of real numbers which is bounded above, okay. And let bi is the supremum value of E, that is least upper bound for E. Then the result says that bi will be a point of closure of E. Closure of means set E together with its limit point is the closure set. Okay. Hence, bi belongs to E if E is closed set. Okay. So, obviously, when E is closed set, E bar is equal to E. So, this result second part follows immediately, then nothing. The first part we wanted to show first. So, that E is a non-empty set of the real number which is bounded above, and supremum of E is B, suppose y, then bi will be a point in E bar. Now, since E bar is a basically E bar is the union of E and E dash, where E dash is the set of all limits points of E, collection of all the limits points of E denoted by E dash. Now, if bi belongs to E, then obviously bi will be the element of E bar, because it is a union of this and bi bar. So, nothing to prove. So, let us suppose bi is not in E, but bi is a limit point of E. Assume we will show then bi is a limit point. So, assume bi is not in E, but we wanted to show bi is in E closure. It means bi must be a limit point of E. So, that we wanted to prove. So, let us seek for every h greater than 0, there exists then a point, say x belongs to E, there exists a point x belongs to E such that bi minus h less than x less than y holds. Why? Here this is our set, say by E, this is the set E, the point bi is not in E, it is outside of it. Then we can find for each h greater than 0, we can find at least some point which lies in the interval, say this is bi, in between bi minus h to bi. This point x will always be available. Otherwise, if it is not so, then bi minus h will behave as a upper bound for E, if it is not so, and this is true because otherwise bi minus h will act as an upper bound, least upper bound for E, as a least upper bound of E, which is not true, because bi is given to be the upper bound. So, as soon as you take a number slightly lower than this, then this number must be available. It means, in between bi minus n and bi, one can always get at least one number of x E which is available. But what is the bi minus by n? But this interval by minus h, is it not where x lies? So, is it not a neighborhood of bi with radius, say h? It is the left hand neighborhood, left side neighborhood of bi in h. So, there exists a neighborhood of y which includes the point of x. It means every neighborhood of this y will includes at least some point of E. So, this shows that, but this is the neighborhood, is a neighborhood of y with radius h, in which the point x is in E, in which there exists a point x in E. So, this shows that y is the limit point of E, because the definition of the limit point of the set M is every neighborhood around the point y, every neighborhood of y, however small radius may be, must include the points of E. And this is true here, that if we take any neighborhood of y, at least one point x is available. Otherwise, if it is not available, then it will contradict to the fact that y is the supreme value of E. So, if it is a limit point, then y must be the point in the closure A dash, hence y is in closure of this set. So, this proves the result. Okay. Now, remark we can see. We know if E is a subset of y is a subset of x. Suppose where x is a metric space. Then we have seen that a set may be open in x, may be open in y, and may not remain open in x. This we have seen just like a open interval a b, which we have seen, it is open in R 1, but it is not open in R 2. So, in case of the open set or closed set, the space which encloses the set is important, where the set is E is open. So, that is why we can introduce the concept of an open set relative to the space, relative to y or relative to x. So, we introduce here two definition, that one is a set E is open, a set E is open, subset of x, means to each p belongs to E, there is associated a positive number R such that the condition d of p q is less than R, where q belongs to x, implies that q is in E. Then we say E is open with respect to x. Open subset of x means then E is said to be open relative to x. Similarly, we can say by, since y is also a metric space under the same metric topology D. So, E may also be open with respect to y. Then we say define that the set E is open, the set E is open relative to y, by D or is a metric space by D if to each here also x d we will write x d is a metric space, okay, relative to x by relative to y if to each p belongs to E, there is there is if there is associated an R greater than 0 such that the condition D of P q is less than R, q belongs to capital Y, imply that q is in E. Then we say it is a. It means what? Suppose we have this set X D, which is a metric space. A set E, this is a set E. We say it is open in X, means that if we take any point P in E, then one can always find out a neighborhood around the point P or a ball centered at P with suitable radius, say R, such that all the points inside this is a point of E. Then we say that E is open in all the points Q which are of X, all the point Q which are in X. If they are the point of E, then we say it is a open. It means that every point is an interior point with respect to X t. But when you say this is our Y is a subset of X. So, it is also a metric space with respect to D. Then we say that E is open with respect to Y. Now, here when you draw the neighborhood around the P, then the point Q which you are choosing must be a point of Y, okay? Because you are not getting the point. Of course, the point of Y is also the point of X, but there may be some point which are in X, but not in Y. So, this relation, when the distance of P q is less than R and Q belongs to Y, implies if Q is in E, then we say E is open in Y. So, as if there is no X, only E is a subset of Y and E will be the open set in Y. Every point of P is an interior point with respect to Y. That is all. Then we say E is open relative to Y, similarly E is open. Now, this has been shown that a set E may be open with respect to Y subset, may not be open with respect to the large set, and that examples we have seen. However, in case of the compact set, we will see this result, this restriction is not there. So, that is more friendly than our open set or closed set. So, that is the idea. Okay? So, we will see that. Before going for the compact set definition, we have one more results. That result shows what will be the form of the open sets in the relative case. Suppose Y is a non-empty subset of X, X d be a metric space, where X d is a metric space. Let X d be a metric and Y be a non-empty subset of X. A subset E of X, a subset E of X d is open. A subset E of X d, a subset E of Y. I am sorry. So, I will subset E of Y d. Let it be Y d, a subset E of Y. A subset E of Y is open relative to Y, if and only if E can be expressed as, or E can be written as Y intersection G for some open subset G of X. So, what this result says is, let X d be a metric space and by is a non-empty subset of X. So, by under the same metric D will also be metric space, and suppose E is a subset of by, then we say a subset E of by will be open with respect to y or relative to y if E can be expressed into this form for some open set G of X. If and only if, that is, if E is of this form, then E will be a open set subset of by, and if E is open, then it can be expressed into this form. So, vice versa. Let us see the proof of this. Okay. Suppose E is open related to y. E is open relative to y. We wanted to show E will be of this one. So, by the definition of the relative to y means to each p belongs to E, there is a positive number say our R p such that the condition D of P q less than R p, where the q belongs to y, implies that q will be in E. This is by definition when E is open relative to y. Okay. Now, let us consider B p as the collection of all such q belongs to X such that distance from P q is less than R p, where q is in the elements of y. Let us q is in X. So, this is already there, q is in it. Let us see. Now, obviously, this is a neighborhood. So, once in neighborhood, it is an open set. And G, if I take the union of all these B p, where the p belongs to set E, then this collection of the open set will also be open. So, it is an open set, is an open subset of X. Clear? Nothing to. Now, since P is in the neighborhood B p, which center P and radius say R p, P is in the, for all P belongs to E. This is by construction, because P is the center of this neighborhood. So, it is clear that E will be contained in G, which is G intersection by. Because this B p is a set in E, and all the points in E belongs to B p, and G is the union of B p. So, E, every point of E is in by as well as in G. So, it is intersection of this thing is obvious. By our choice of B p, we can say we have that B p intersection by is a subset of E. By our choice means, because we have B p constructed like this way, set of all such that this is there is a positive such that this one is. So, when it restrict q to y, then all these points basically they are the points common to E, intersection with this and contained in E. So, by our choice, because this will be the set, to each P there is a positive, because E is open, because E is an open set. So, this entire thing is available in E, because E is giving to be an open set relative to this. So, this is by our choice. Therefore, for every P, so the G intersection by, take the union of this, G intersection by is contained in E, and hence E will be equal to G intersection by. So, one result is complete. Conversely, just one more. Conversely, if G is open in X and E is of the form G intersection by, then every P belongs to E, every P belongs to A has a neighborhood B P, which is totally contained in G, because G is open and E is of this form. So, E will also be for any P belongs to E means it will be in G, and G is open. So, neighborhood must be available in G. Then the G B P intersection by neighborhood intersection by will be contained in E. Okay. Because P is in there and G is this form. So, intersection will be available in E, so that E is open. So, that E is open relative to Y, by relative to Y, and that is prove the results. Okay, thank you very much. Thanks.